The second sequence of part of this workshop on estimation is about estimating suprema and infima. So we have, and the expressions that I will look at, they could be suprema over a set. It applies quite generally, but suprema over some objects of some function on those objects, and infima over some objects. And we want to come up with upper bounds or lower bounds. With suprema, one has to be a little bit careful whether we have a strict or non-strict inequality. And I'll mention that briefly. So let's see. How do we come up with upper bounds, and what does it mean to have an upper bound? So if you want to come up with an upper bound of L for supremum, what this means, supremum is the least upper bound. This, and anything above it has to be an upper bound. So being above the supremum is like saying that, this is the same thing as saying that for all x in your set of interest, f of x is less than or equal to L. A lower bound, on the other hand, means that if we say that the supremum is bigger than or equal to some other value, let's call it A, then this means that, well, and this is where the less than or equal to comes into play, is that that means that if we go a little bit below A, it cannot be a lower bound. So for all epsilon positive, there exists an element x in x such that f of x is strictly bigger than A minus epsilon. So it's the difference between working with upper bounds and lower bounds is existential quantifiers and the fact that we need for all. If we have a little bit of room, so we have strictly less than A, we can just say that there exists an element A x with fx bigger than A. So strict inequalities are a little bit easier to work with. Otherwise, we have to kind of force an epsilon in there. Now, infimum is morally the opposite of the supremum, and indeed, infimum would be minus the supremum of minus f. So if we are to get lower bounds for it, that's exactly like getting upper bounds for supremum. And this corresponds, well, saying that something is a lower bound means to say that for all elements in the space, f of x is actually bigger than or equal to L. Whereas upper bounds are, in a sense, the harder ones because they mean that for all epsilon positive, there exists an x in your set such that it lies between f of x, A, and epsilon. So it lies between f of A, the infimum, and the A minus epsilon. So when you're proving an upper bound, you're actually proving something like this. When you're proving a lower bound, you're actually proving something, you're finding an element where you have a bound. And often the similar tools for sup and inf apply. So I want to give an example of this that explicates kind of both of these simultaneously in a difficult way. So suppose AK would be bounded and BK would be bounded in between 0 and m for some m and all integers. Now, suppose we took the supremum over all natural numbers. I'll modify this statement a little bit so we get something simpler to work with. And then we take an infimum over all those numbers and the supremum of all those numbers. Then we get that essentially the largest product is bigger than or equal to the smallest AK times the biggest BK. Now, there's a way of looking at this. Again, we have to ask ourselves the three questions. What are we bounding? How are we bounding it? So up or down? And what do we know? So in this case, the 1 and 2 will be more important. These are not always as important. So depending on whether you look at this from the left or the right-hand side, it's important to look at both. You see that we are bounding actually differently. So on the left-hand side, we are bounding sup k supremum from below. But from the perspective of the right-hand side, you can think that we are bounding infima ak from above, because we have a product of two positive things. We're really bounding suprema of bk from above and suprema infima of ak from above. So in this estimate, we will somehow need to touch upon a lower bound for supremum and an upper bound for infimum and supremum. And well, how will be, so lower bound there and upper bounds for these. And what do we know? Well, in this case, we know very little to start with, other than that these all are finite numbers. We know that they're also positive because the numbers are non-negative, because the numbers are non-negative. So let's look at, there's a setup and choices. Again, I will not focus on these parts now. Setup would be just assuming that we have AK and BK and M, such as in the statement. So let's go up here. So we want to, let's focus first on the lower bound. So we want to give a lower bound for supremum of something. So we will need to use this existential thing. So there will be a choice, well, or fixing, call this step the quant. So let's fix an epsilon positive and arbitrary. And we want to show that the supremum over the product is bigger than or equal to the left-hand side here. But to do that, we have to say that there exists a k in natural numbers such that ak bk will be bigger than or equal to the infimum over k, natural numbers, times the supremum over b, natural numbers, minus epsilon. We want to show this. We want to find an index like that. Well, let's look at now this bound. We have to choose this k wisely. So let's look at this estimate now. We want to estimate AK, BK from below by things like this. Well, and here it's useful to know that we're also working with an upper bound for inf and an upper bound for sup. And we wanted to use something in terms of AK. Well, the useful thing here is that inf is always less than or equal to AK. Now we don't need to go through this argument now, because an additional argument that we can use is that inf is always less than or equal to AK. So we want to go down, we want to get an inf here. So AK is less than or equal to inf of all the numbers. And let's put an n here so that we don't mix up the number indices that we're using. But now we have a supremum here, and BK is not less than or equal to the supremum. This is not less than or equal to the supremum. But we can use these facts here. So let's see what did we use? We used some additional facts. So inf of a function is always naturally less than or equal to any particular function value. And similarly, sup would be bigger than or equal to, naturally bigger than or equal to a function value. But another thing, if we want a lower bound by some element here, we can bound it from below by fx minus epsilon for some x. And we can bound the supremum from above by fx plus epsilon for some x. So this is for all x, we have that bound, but then on the other side we will have some. And how is this proven? Let's just remember, recall this a little bit. Well, if we take the supremum minus epsilon, this is not an upper bound. That means that there exists an f of x that lies above it, and then we put the epsilon on the other side. And similarly for inf. So if we apply this other way of looking at it, then bk here, we can choose a k so that what we get here is supremum kn bk minus some epsilon prime. So let's choose epsilon prime, and we'll say like this soon, and a k such that bk would be bigger than or equal to the supremum over all k minus epsilon. And we have to do this choice because we're going, again, kind of the wrong direction. But now let's spread this out. Infimum an, supremum bn, and I'll switch an index again, minus epsilon prime infimum an. And okay, here we would like to put epsilon there. We'll have to do a little choices. So we'll set it as epsilon infimum over infimum an if infimum an is not equal to 0. In that case, we will get exactly the inequality that we want. By the choice of epsilon prime and k. But we have to add a little check. If infimum an is equal to 0, the inequality is immediate. Why is that? Because the right-hand side is equal to 0, and the left-hand side is a supremum over positive numbers. So this left-hand side is always bigger than 0, and the right-hand side here, if it's 0, then it will automatically be true. So the case when this calculation is not valid is actually automatic. So again, we have our same questions, 1, 2, 3. The number 3 didn't show up quite the same. But what we were using was that if you want to have an upper bound, what you mean is you prove for all. You want to have a lower bound for supremum. That means for every epsilon, you find some element. So we use this fact here to prove a lower bound. And then another way of using infima is that infima is always less than all the elements, suprema is always bigger. But then in the other direction, you can always find an element that's a little bit bigger and find an element that's a little bit smaller, up to an addition. And using these, we can choose this bk so that it's very close to the supremum. And that is the choice that we make here. We're using everywhere that everything is positive because we are multiplying the estimates together. And this is where we get that, and the choice of epsilon prime allows us to get epsilon.